For example 1, we want to sketch the graph of 1 divided by x plus 5 plus 2. And the way we're going to do that is by using the asymptotes, the horizontal and vertical lines that this graph approaches. So you might want to look at this first in Desmos or on a graphing calculator, but what we talked about in class is if you have 1 divided by x plus 5 and then let's say plus 2 at the end, this is a transformation of the graph of 1 over x. It in fact goes left 5 places and then it goes up 2. And if your vertical and horizontal asymptotes both start at 0, I'm going to draw in the location of them on my new graph. So if we go left 5, at negative 5, there's going to be a vertical line. It's not a part of the graph, it's just that the graph approaches it. And then also, for positive 2, we're going to have a horizontal asymptote. So this is y is equal to 2, and this is x is equal to 2. So those are the two asymptotes for this graph. So it should be that the graph drops down like this, and then approaches from the other side. So the idea is it gets really, really close to both of these asymptotes on both sides of the graph. And that is it. So this is a basic sketch of the graph of 1 divided by x plus 5 plus 2. For example 2, same idea. I have a rational function. It looks a little bit more complicated than the previous one. There's not two pieces, there's just one piece. But I want to take the same approach. I'd like to find both the vertical and horizontal asymptotes, plot those, and then sketch the graph of this and around it. So for this example, I'll only do this once, but I want to actually divide. I mean, this is telling me to divide x minus 3 into 2x plus 4. By doing this, we're going to write this equation so it looks more like something in example 1. So let me set that up. So we have x minus 3 divided into 2x plus 4. When I do this division, I'll put a 2 here because that gives me 2x minus 6. And when I subtract this, I'm left over with a remainder of 10. What this all means is the fraction 2x plus 4 over x minus 3, it's exactly the same thing as, well, we divided out 2, but we have 10 out of x minus 3 left over. And written this way, I can see that, oh, at x equals 3, I'm going to have a vertical asymptote, and at y is equal to 2, I'm going to have a horizontal asymptote. So I'm going to plot those on my graph. So here is y is equal to 2, and x is equal to 3. So I know that the graph has to approach these two places. Y is 2, and x is 3. So now I'm just going to sketch in the graph around it. Now, there's this positive 10 over here, but all this is doing is stretching your graph. If it was negative 10, it would have flipped the graph upside down. Okay, so here is my sketch. It should look something like this. Again, it doesn't have to be perfect, just an idea of where the graph is going. And then we'll have a piece over here, like this. So like I said, we don't want to have to divide every single time to figure out what the horizontal and vertical asymptotes are. But there's actually a really simple way if you look at this graph to figure it out. So I see there's an x minus 3, and any place where the denominator is 0 and you can't cancel a factor, you can just look at this x minus 3 and say, oh, well, x equals 3 is the place where it's 0. This has to be a vertical asymptote. So I'm going to use that as a fact as we go forward here. The place where the denominator is 0. If I can't simplify the fraction, it's got to be a vertical asymptote. Locating the horizontal asymptote isn't as obvious, but you can figure it out by looking at the original graph as well. Where that comes from is the numbers in front of the x terms. So we had a 2x and a 1x. If you look at the ratio of those two numbers, it'll give you the horizontal asymptote. And the reason that works is by looking back to the division that we did over here. We wanted to cancel this 2, and there was a 1 here, so we had to multiply by 2 to get a 2x. That's the same thing as saying there's a 2 here, there's a 1 here. I know when I divide, a 2 is going to come out. So like I said, you could divide every single time to get this number, but it's really fast just to say, oh, it's a 2, it's a 1. The ratio of those two things has to be my horizontal asymptote. So at least we're like kind of going in a faster way to figure out where things are located on the graph. So at this point, you should be able just to look at the original function and say, oh, 3, that's a vertical asymptote. 2 divided by 1, that's the horizontal asymptote. And for the last example, I want to sketch a graph of this rational function 3x minus 5 divided by x plus 4 using some of the facts that we had in the previous example, but I want to add a little bit more to this problem. I not only want to locate the asymptotes, but for a more accurate sketch, I actually want to figure out where this thing crosses the x-axis and the y-axis. So I'm going to list those things out off to the side. So I want my horizontal asymptote and vertical asymptote, but I just want to do a quick discussion on where's the x-intercept and also where's the y-intercept. From our previous work, the horizontal asymptote, it's got to be y is equal to, in this case it's going to be 3 divided by 1, or if you want, just 3. And where that is coming from is the 3 and the 1 in front of the x's. The ratio 3 over 1, if I were to divide, would give me a 3 all by itself. I can quickly just say y equals 3 is the horizontal asymptote. If I want the vertical asymptote, the denominator needs to be equal to 0. I know if I put a negative 4 in place of x, that'll do the trick. So x equals negative 4 is the vertical asymptote. If you want a couple of other things, like where it crosses the x-axis and the y-axis, that's actually not very difficult either. I'll start with the x-intercept. That's going to be wherever your numerator is equal to 0. So you could actually set up the equation 3x minus 5 is 0. And just stop to think about it for a second. If the numerator is 0, the entire fraction has got to be equal to 0. In this example especially. So the x value where that happens is going to be by adding 5 and dividing by 3, 5/3, or more specifically, at 5/3 for x, you're going to get 0 back for y. So we'll plot that in a second. And for the last thing, the y-intercept, we use, let's see, the ratio of the first two terms. It turns out that the ratio of the last two terms is going to be the location of the y-intercept. The reason for that is you're taking the value 0 and you're plugging it into the function. And what is left over is going to be 0 minus 5 over 0 plus 4, and that's just negative 5/4. So this is the point 0 for x, negative 5/4 for y. These four things will really help us get a better sketch of this graph, but just to recap, the place where the denominator was 0, that's a vertical asymptote. The place where the numerator is 0, that's an x-intercept. The ratio of the first two terms, that's the horizontal asymptote. And the ratio of the last two terms, that's going to be a y-intercept. I'm going to plot all of these things and sketch in the graph around it. So I'll start with y equals 3, that's my horizontal asymptote. Negative 4 for x is my vertical asymptote. This thing has an x-intercept at 5/3, and that is approximately, let's see, 5/3, that's about 1.7 about, so just get a rough estimate that that's like right about there. And it also has a y-intercept of negative 5/4, which is negative 1.25, so that's roughly here. So I know my graph, it has to go through these 2 points and approach both of the asymptotes. And then on the other side, it has to approach the asymptotes like this. I know that it couldn't be below because it would cross over the x-axis again, but this is just a more accurate sketch by using a couple of other features on the graph.